Hi everybody. Let's spend a few minutes here talking about derivatives. So this is probably going to be pretty much familiar, although maybe not 100% to just about everybody, but I think it's still worth reviewing. So in particular, I'm going to be interested for the most part here today in derivatives when we have a function defined on Rn, not just on R. So let's say we have a function and the function is defined on Rn, and as usual when I write this, if we're not being pretty specific, then everything that we do holds if we're actually working with a function that's defined on just some open subset of Rn. It would work in that subset. So the first thing we want to talk about here partial derivatives. And again, I'm going to go through this fairly quickly because I think it's probably for the most part review. So partial derivative of f with respect to, so we have to take the derivative with respect to each of the n variables. So again, we do this, evaluate it at some point, and I'll just say that's x bar here. And so, of course, this is defined identically, really, to the derivative when n is 1, when we have a real function. And so this is the limit. So I say it's defined identically, but it is, but we'll see that it looks a little different perhaps. So this is 1 over t. So already it looks a little different. I haven't put delta x down here. And then I have f at x bar plus t times e sub I, let me come back to that in just a moment, minus f of x bar. So this looks the same as our definition of the derivative for a real function when n is 1, except that instead of having a delta x in the denominator, now, and having delta x over here, now I have t times the ith unit vector. Now remember that the unit vectors are, well, e sub 1 is the unit vector that has a 1 in the first component and zeros everywhere else. E2 is the unit vector that has a 1 in the second component, zeros everywhere else, out to e sub n, which is the unit vector that has a 1 in the last nth component, zeros everywhere else. So instead of delta x here, I have t times the ith unit vector, because we're doing this with respect to the ith variable. And the reason that we have to do that is that we do have here a vector in n space, and we're adding to it a vector. So this is a unit vector. It's in Rn. In fact, let's emphasize that by writing here that everything in here has to be, of course, in Rn, because f is defined on Rn. And so the issue is we could still put a delta x in here and have this be x bar plus a vector, delta x, but the problem is I can't divide by a vector. So instead of putting a delta x down here and saying, well, I'd like to divide by delta x, but I can't divide by a vector, instead we put the vector over here, and instead of writing it as delta x, we take a particular delta x, that is a multiple of the ith unit vector, and then we divide by that multiple. We divide by t. So conceptually, really exactly the same as the derivatives we have done before. And let's note too then that in fact what I'm going to do here is I'm going to write g of t, and I'm going to define that to be f of x bar plus t e sub I. So that's just this. Notice that when t is 0, this is this, but g now is a function that's just, it's a real function because the t here is a real number. So I've converted this right-hand side into this here, into a real number, and that would be, and let's write this, limit t goes to 0 of g of t minus g of 0, where g is defined to be this real function over here. And of course, notice that that is exactly the derivative of g, the real function g, the derivative of g at 0. So it's as if I've now said, let 0 be the real number x bar, and this is now that x bar plus t, which would be the delta x. So this is exactly the derivative of g at 0. In fact, let me even write, no, I'll just write, yeah, I'll write it as at t equals 0. It's the derivative of g at 0. And that doesn't look like it's particularly useful at the moment, but it is going to be useful in a couple of moments, okay? So that's our definition of a partial derivative. Again, I assume that's pretty familiar to everybody. And we also then have the notion of the gradient of f at a point x bar in the domain. So here, again, I'm leaving out partial derivative of f at x bar, gradient of f at x bar. This is defined, that's the notation we use, and if it's the gradient evaluated at the vector x bar, then this is just the vector whose components are the partial derivatives. So it's just the vector of partial derivatives. And let me actually put in here the x bar, because I want to emphasize that this is a number and it's evaluated, it's the derivative evaluated at x bar. And there are n components because there are n partial derivatives. And so this, of course, is a number, so let's write it as element of Rn. It's a number because the x bar is a fixed given number. But if I let x bar be a variable, if I think of it as varying, then this gradient could be written as a function. So I could write this as like this to emphasize that it's a function defined on the domain Rn, and it picks out a vector of n components, each of which is a real number. So this function maps from Rn into Rn, because for every point in Rn, it picks out the gradient vector in Rn. So we have a partial derivative, we have the gradient, and let me put lines under these just so I can see where things start and stop. And so now let's look at the directional derivative. And the directional derivative tells us basically the same thing as the partial derivative, or really the derivative for a real function. It's kind of like the slope, rate of change. It tells us this for movements away from x bar in any direction in Rn, not just the unit vector directions. So let's say we're going to have v here be not the origin, be a vector in Rn. And so our directional derivative is telling us the derivative of f in the direction v. And so the notation we use for that is the same kind of notation we've had before. And again, I'm going to write x bar to emphasize that it's being evaluated at some point in the domain. And that is, by definition, the limit as t goes to 0, 1 over t f x bar plus t times v instead of ei minus x bar, f of x bar, sorry. Okay, so notice this is just a generalization of the partial derivative. The partial derivative is defined for the n different directions defined by the unit vector, the n unit vectors. So this partial derivative is the derivative in the direction of the ith partial, of the ith unit vector, the ith component in Rn. And this just generalizes this to say we can take the derivative and evaluate the rate of change or the slope in any direction in the domain. And in fact, let's even draw that down here. Let's suppose that this is x bar, and so let's suppose that this is x bar plus v. So v is the vector going off a little bit above the first unit vector direction, and let's say for some t, let's say this is t times v. For some t, well, that's not working out very well. Let's say for some t between 0 and 1. And so that v could be any direction. And of course here, this is of course in the domain R2. And the v could be any direction here. And notice again that this would be the derivative of a function g at 0. Maybe if I want to do the same thing I did up here, I'll say where t equals 0. Again, now where I'm going to define g the same way as here, but I'm going to replace the ei with v. So where g of t is just f of x bar plus t v. Okay, so 3 derivative concepts in Rn, generalizing from derivatives of real functions, but using the same idea. So it really is a generalization. In fact, we're even converting things into real functions here in both these cases. So the directional derivative, you might say, well, how do I find out what this directional derivative is? How do I evaluate, compute, if you like, the directional derivative of some function that I get in some direction v? I know how to do it for partial derivatives. I just set all the other variables as fixed, and I think of this as the only variable, and I just take the derivative as if it's a real function. Okay, so how do I evaluate this? Well, let's go over here and see how that might work. So let's note that defining g this way, we have g of t is f of x bar plus t times v, but I'm going to write this out component by component here. So this is plus t times v1. Same thing for the second, third, fourth components out to the nth component. And notice that I've got the n components of the x vector, the x bar vector, which is the base from which I'm at which I'm computing the derivative. And the v is also a vector. The v is a vector in Rn. It's a squeezed in n there, but that's supposed to be Rn. And so the v also has n components. And so x bar plus t times v is first component, x1 bar plus t times v1. So all we're doing here is just vector addition and scalar multiplication. And so if that's the g function, then what do we have for g prime as a function of t? Again, that's a real number. Well, the chain rule, of course, tells us that this is going to be just the derivative of f with respect to the first component times, I'm taking the derivative with respect to t, so that would be just the number v1. So v1. Let's do the second one, second component. So this would be the partial with respect to x2 times, now it's not, I didn't write it in here, but this would be times v2 out to the derivative with respect to xn times vn. And so here I've done something that we do all the time. I have left out the argument in the partial derivatives here. So, but that's implicitly in here. If we're doing this at x bar, then this is the first partial derivative evaluated at x bar, second partial derivative evaluated at x bar, nth partial derivative evaluated at x bar. And so this is just these factors in the terms of the sum. These are just the components of the gradient vector. And the v's, of course, are just the components of the v vector. So this sum is actually just the gradient of v, and now I will put back in the x bar here, dot product with v. The first component of this times the first component of this, second, add up the various products of the two components. So this actually is a kind of a theorem, but it's pretty trivial here. So this really tells us, well, let's back up here a little bit. Let's back up a little bit. I've got this, but notice that I defined this to be g, so this is g prime. This is g prime of t, and it's actually g prime at t where t equals 0. So we should put in here, this is where t equals 0 if this is evaluated at x bar. And if that's g prime at t, that's this, that's this. So this is actually then the directional derivative in the direction v at the point x bar. So this tells me that I can evaluate this directional derivative by simply taking the gradient at x bar dot product with the direction v. So that's something that we're not going to make use of today, but again, I want to go through the development where we review several ideas about derivatives. So this fits in really well here with what we've done before and what we're going to do coming forward. We will come back and see this later on in the course, but we're not going to do any more with this particular idea today. Now, what I want to do is look at higher order derivatives when we have a function defined on Rn instead of just a real function. And of course, what we're doing here is we're generalizing to Rn, the idea of higher order derivatives for a real function. So for a real function, we all know about not just the first derivative, which is this, but for a real function, well, I guess it would be like this. This is a real function. But then, of course, we know about the second derivative, which is just the derivative of the first derivative, and the third derivative, which is just the derivative of the second derivative function, and higher order derivative functions. And when they're evaluated at some point, then they're the higher order derivatives evaluated, they're their numbers. So let's look at higher order derivatives for functions defined on Rn. So higher order derivatives. So here we, for the second order derivative, or the second derivative of f, we say with respect to any one of the variables, but then we take this with respect to another variable, could be the same variable. And so this is defined, of course, to just be the derivative of, the partial derivative with respect to xi of the partial derivative with respect to xj. I should have put in here x bar as well. Again, I just do that to emphasize that when we work with a partial derivative or a second partial derivative, we are working with a number almost always. Now, we do have a function here. This is a function of the argument here, but when we actually work with the second derivatives, we work with them evaluated somewhere, and when the derivative, the first derivative, the second derivative is evaluated at a point, then that becomes a number. And so I have put the x bar in here most of the time just to emphasize that fact. Okay. Now, there is one thing that I actually left out over here, and I was about to leave it out over here, but so it struck me that I need to actually not leave it out, and that is, and let me go over here and say, this partial derivative is this limit if the limit exists. There are going to be functions, just as there are real functions that aren't differentiable, the derivative doesn't exist, there are going to be functions on Rn for which the partial derivatives don't exist. This limit doesn't exist. So of course, we only define this to be the derivative when it's there, when it actually exists. And the same is true down here. Here again, we should have said if the limit exists, and here as well, if the limit exists, and of course here you can say, wait a minute, I don't see any limit in here, but of course the limit's in there because this is the derivative, the partial derivative of this function evaluated at x bar. So that means this is defined as this limit, and of course this is in turn defined as this limit. So if this limit exists, and I guess we could even say if the limits exist, if this limit exists and this limit exists, then we have our second partial derivative. So there are going to be situations where they don't exist. Let's even say there are going to be, just as there are situations for real functions, when the domains are, there are going to be situations where the derivative exists, but the derivative function isn't continuous. And so that happens for real functions, and it can happen for functions on Rn, and for real functions, we say the function is differentiable if the derivative exists. For functions defined on larger dimensional spaces than just R1, we actually, the terminology we use is that the function is differentiable if the derivative exists and is continuous. So this is defined just fine. This is not a problem. This is defined and this is defined if the limit exists, but we don't actually say the function's differentiable here. We say the function's differentiable if the limit exists and this function is continuous in the neighborhood of x bar, or on the open domain here on which this is defined. And so same is true for higher order derivatives, and in fact we even say that we say f is a ck function for k1 or k2 or k equals 3 is a ck function if all k order derivatives exist and the derivative functions are continuous functions in the domain in which we're working. So in particular then, this would be a C1 function if these n partial derivatives all exist and they each one is a continuous function of the variable here. These derivatives, we would say the function is C2 if every one of these derivatives, of which there are, of course, n squared, if we're in Rn, so every possible combination of I and j, so there are n squared of these derivatives, and if every one exists and is a continuous function of the variable, then we would say that this function is a C2 function. Now, I said that there are, of course, functions that where the derivatives exist, but they're not continuous functions, where the limit exists. Those are fairly unusual. You are not going to run into those functions very often. So in particular, so long as the function that we're working with, the function f, is made up of functions that is the sum or the multiples of functions that themselves are continuously differentiable. And by the way, we say in this case that are k times continuously differentiable. Then the function f is going to be continuously differentiable as well. So for example, if I have, well, we're going to look at a function, maybe a couple of functions in just a few moments that will give us a good example of this. So I won't go there right now, but we'll come back to that in just a few minutes. So we have all of this, and so what we want to do next is, in fact, the only remaining thing to do for right now is to look at something called the differential. And so let's take off what we have here. In fact, I think we can pretty much take everything off, and then we will look at something called the differential. This, again, may be familiar to you. For many of you, it may actually not be that familiar. So let's take this off, and then we'll do that. Okay.